You are welcome to the lecture number 1 of the course DME 207, that is Materials and Metallurgy. This lecture of DME 207 will cover the topics like Introduction to Engineering Materials, Importance and Usage of Engineering Materials, Classification of Materials, and Introduction to the Properties of Materials like physical properties, mechanical, electrical, thermal, and chemical properties. We will cover all these topics in this course, starting with the introduction of engineering materials, that how the engineering materials come into the life of human beings and how it further took an important place into the human civilization. As we know that materials are so important in the development of human civilization, the historians have identified early periods of civilization by the name of the most significantly used materials. Like at the very primary stage, human uses the stones to make their shelter, weapons, etc. That's why that age was known as Stone Age. And afterwards, the civilization, as they adopted the new materials and invented new type of materials, the further civilizations were nominated by the use of different materials like Bronze Age, followed by Iron Age, Space Age, Electronics Age, etc. This is just an observation made to showcase the importance of materials and their impact on human civilization. It is obvious that materials have affected and controlling a broad range of human activities through thousands of decades. Coming to the Stone Age, that was very early stage when human beings come in contact with any kind of material. In this age, people used only natural materials like stone, clay, skin, and wood for the purpose like to make weapons, instruments, shelter, etc. Thus, the sites of deposits for better quality stones became early colonies of human civilization. Moving forward to Bronze Age, which came into light around 3000 BC, the increasing need for better quality tools brought forth exploration that led to Bronze Age, followed by Iron Age. When people found copper and how to make it harder by alloying, the Bronze Age started. The use of iron and steel, a stronger material that gave advantage in wars, started about 1200 BC. Iron was abundant and thus availability is not limited to affluent. This commonness of material affected every person in many aspects, gaining the name as material. The next big step in human civilization was the discovery of a cheap process to make steel, which enabled the railroads and the building of modern infrastructure of industrial world. One of the most significant features of the democratic material is that number of users just exploded. Thus, there has been a need for human and material resources for centuries, which is still going strong. Coming to the next forwarded age, that is known as space age. It is being said that and agreed that we are presently in space age, marked by many technological developments towards development materials, resulting in stronger and light materials like composites, electronic materials like semiconductors, materials for space voyage like high temperature ceramics, biomaterials, etc. If we summarize the findings of these civilizations in respect of materials and their utilization, then Iron Age brought the tools and utensils, Steel Age brought railroads, instruments, and the Industrial Revolution. The Space Age brought the materials for stronger and light structure, that is, composite materials. The electronic age brought semiconductors and thus many varieties of electronic gadgets. Coming to the next point, that how the materials were used in technology and how it affect the current life of human beings. As engineering materials constitute foundation of technology, it is not only necessary but a must to understand how materials behave like they do and why they differ in properties. This is only possible with the atomistic understanding allowed by quantum mechanics that first explained atoms and then solids, starting in the 1930s. The combination of physics, chemistry, and the focus on relationship between the properties of material and its microstructure is the domain of material science. The material science is a subject which must be studied by each and every engineer irrespective of their domain. As far as all engineers need to know about materials, even the most immaterial like software or system engineering depend on the development of new materials, which in turn alter the economics like software hardware trade-offs. Increasing applications of system engineering are in materials manufacturing and complex environmental systems. Innovation in engineering often means the clever use of a new material for a specific application. For example, plastic containers in place of age old metallic containers. It is well learnt lesson that engineering disasters are frequently caused by the misuse of materials. So, it is vital that the professional engineers should know how to select materials which best fit the demands of design economic and aesthetic demands, as well as demands of strength and durability. Beforehand, the designer must understand the properties of materials and their limitations. Thus, it is very important that every engineer must study and understand the concepts of material science and engineering. This enables the engineer to select a material for a given use based on consideration of cost and performance. To understand the limits of materials and the change of their properties with use, to be able to create a new material that will have some desirable. Moving further on to the classification of materials. Basically, the materials at very primary stage are classified in two ways. One is the metals and other non-metals. The metals part comprises of the elements like cast iron, steel, copper, zinc, silver, gold, tin, etc. And non-metals have wood, plastic, wax, clay, ceramics, composites, thermocol, etc. The metals and non-metals are basically differ from each other that by the by the finding of elements like iron and carbon. If any substance have both the iron and carbon constituents, that falls under the category of metals, and the element or substance which do not have iron content falls under the category of non-metals. Further, metals are classified as ferrous metals and non-ferrous metals. Ferrous metals comprises of cast iron, steel, wrought iron, etc. And non-ferrous metals have brass, bronze, nickel, silver, gold, etc. etc. Further, non-metals are classified as polymers, composites, and ceramics. Polymers have polyethylene, polystyrene, polypropylene, polyvinyl chloride, etc. And ceramics have clays, silica, feldspars, etc. So, moving on to the onto the material classification and metals and non-metals, and further metals as ferrous and non-ferrous metal. If we go on to the short definition of the ferrous and non-ferrous metals, then ferrous metals are those metals in which iron is their main constituent. All type of steel comes under ferrous metals. For example, cast iron, steel, galvanized iron, and wrought iron, etc. And the non-ferrous metals are those metals in which metal other than iron is as their main constituent. For example, lead, copper, zinc, brass, tin, etc. falls under the category of non-ferrous materials. Non-metals are like glass, plastic, rubber, Teflon, composites, etc. etc. Further, one more category of metal which comes by the by mixture of metals and non-metals in an appropriate ratio. Alloys are the mixture of metals and some non-metals in such a way that there are at least two metals and other non-metals. That is the stainless steel which have two metals as nickel and chromium makes an alloy. Moving forward to the properties of materials, we will go for the properties like physical properties, mechanical properties, electrical properties, thermal properties, and chemical one. We will go in detailed study of the properties of material with physical properties as shape and size, dimensions, color, appearance, density, porosity, and structure. Mechanical properties as elasticity, plasticity, ductility, malleability, brittleness, and so on. Next is the electrical properties that have as resistivity, conductivity, dielectric constant, dielectric strength, and thermoelectricity. Moving forward to thermal properties, which consists of melting point, freezing point, specific heat, thermal expansion, thermal conductivity, refractoriness, and heat resistance. And finally, for chemical properties, as composition, corrosion resistance, and structure. We will go with each and every one in detail. Physical properties have first one definition as shape and size. In the first row, I have shown different sizes of elements having the same shape. And the first two element or object have cuboid shape, but their sizes are different. Next two objects like disc having same shape, but their diameter and thickness are varying, that makes differences in their sizes. And third one is the oval having same shape, but the difference in their minor and major axis makes a difference in sizes. The second row shows that the objects having same size but different shapes. The first two element object that is shown as an arrow, their tails have different structure, different shape, that makes difference between these two. And moving on to the rectangles having same size but shape, different shapes, and last there are donut having same diameter, internal and external diameter, but they have different shapes. Moving forward to the next definition of physical properties and of materials, like dimensions. Dimension is meant by the size of any object. It is measured in terms of length, width, height, diameter, radius, etc. It is measured in SI system, MKS system, CGS system. Like for measurement of the length, we use mm as millimeters, cm as centimeter, and meter. For weight, we use kilogram, gram, pound, etc. And for time, it is used second, and so on. Color is the other property, a physical property of any material. It is an important property to identify the originality as well as quality of material. The color of the material depends on the wavelength of the light that material absorbs. Besides this, our a color is introduced into various materials in the form of coloring pigments and dyes to produce attractive artificial color. Moving forward onto the appearance, it includes luster, grains or marks, texture, etc. Luster is the ability of material to reflect light. Texture is the quality of material, like textile materials, cloth, different kind of papers, and grains or marks is the quality of certain high quality planks. Density is an important parameter and physical property which is used to study metallurgical properties of material. How closely atoms are arranged of definite mass in unit volume is defined by the density of that particular object. Numerically, it is expressed as the ratio of mass over volume. Next is the porosity in the sequence of physical properties of material. It defines the voids present inside the molecules during solidification, measured as total volume of void to the total volume of material. Porosity leads to lower the thermal conductivity of material. It is responsible for the dry corrosion in the metals and weakening of ceramic materials. We come to the structure. The atomic or molecular crystalline structure of metals, alloys, and other crystalline compounds are experimentally found out by the X-ray diffraction, neutron diffraction, and field and microscopy technique. Body-centered cubic crystal, that is BCC, face-centered cubic crystal, that is FCC, and hexagonal closed-packed important metallic structures used in the study. Moving forward to the mechanical properties of a material, before going on to the individual definitions of the properties of different properties of material, here I'm displaying a stress strain diagram that is most widely used to explain the different mechanical properties of any material. Here I am showing a stress strain diagram for a ductile material that clearly shows elastic region, plastic region, and different points which we find when an standard specimen is applied by the tensile loading onto the UTM machine. As we increase the loading onto the specimen, it starts to elongate, but up to a certain point, that point is known as the elastic point or limit of proportionality. It regains its original shape and size after unloading the component. That proportionality limit holds good, and the scientist known as Hooke, that he gives a very good definition that strain is directly proportional to stress up to the elastic point. That is, the strain is directly proportional to strain, and that proportionality constant is known as the Young's modulus, and it is represented by capital E, and that is equal to stress divided by strain. Further moving the further enhancing the load over the specimen, we get the yield point, and after that we enter into the plastic region, and subsequently we find ultimate strength, and finally the fracture point of that material. Moving forward on to the individual definition that has been found over the stress strain diagram, and with that, with the help of that diagram, we explain each and every mechanical property of the component. First one is the elasticity. It is the tendency of solid metals to regain its original shape and size from its deformation as soon as the stresses are released. Elasticity is measured in terms of Young's modulus of elasticity, that is represented by capital E, which is equal to the ratio of stress and strain in the form of force, area, and length. We define stress as force per unit area and strain as the ratio of change in length over original length. And finally, we get modulus of elasticity as force into original length divided by into change in length. Plasticity is the tendency of material to get permanently deformed gradually up to the yield point when material is subjected to external load which overcome the elastic limit. Next property is the ductility. Ductility is basically the degree of plastic deformation. It is the capacity to undergo deformation under tension without rupture. It is expressed as a percentage of elongation or percentage of reduction from a tensile test. Better ductile metals can be easily elongated into the wire tubes. Next one is the malleability. It is the ability of metals or alloys to withstand deformation under compressive loading. To make thin sheets, hammering or rolling operation are performed on malleable materials without causing the material to crack. Gold is the most malleable metal and may be beaten into very thin sheets. Brittleness is another mechanical property of the material. It is the tendency of material which do not allow any dimensional change and any kind of plastic deformation into it. Materials that are brittle shows only slight permanent distortion before breaking. An elongation less than 5% in a 50 gauge length is considered as a brittle material. Further moving on to the hardness and creep and so on. Hardness is the property of metal that resists any kind of penetration, scratching, deformation or machinability over its surface. It also tells the ability of metal to cut another metal. It is basically resistance to indentation. Indentation hardness is measured by hardness test like Brinell hardness test, Rockwell hardness test, and Charpy test, etc. Creep. Creep is an important property which is widely used during the design of any machine component or any large size engine. It is a time dependent and permanent deformation of material when subjected to a constant load or stress. Machines such as turbine, rotor in jet engine, steam generators, flywheels, etc. undergo time dependent strain at elevated temperature and pressure that can cause deformation. Next one is the fatigue. Fatigue is a kind of failure in a material or alloys under repeated fluctuating loads. This is an important property noted for the proper maintenance of machine parts, bridges, aircrafts, etc. Fatigue ends with the propagation of crack, and fractures, etc. Stiffness is the property of material by virtue of which it resists any kind of deformation in it against the externally applied load or stress within elastic limit. It is an important property by considering which all types of machine components are designed and manufactured. Moving forward on to the toughness, toughness is defined as the ability of material to withstand bending on the application of shear stress without fracture. It mainly depends on the tensile strength and ductility of materials. Copper is found to have greater toughness than cast iron. It is the ability of material to absorb energy and deform plastically before fracture. Resilience, it is the ability of material to absorb energy up to the elastic limit when it is elastically deformed by loading and releasing same amount of energy upon unloading. Now, coming to the tensile strength, yield strength, shear strength, and so on, the tensile strength is the measure of strength and ductility of the material. Ultimate tensile strength is the force required to fracture a material. Tensile strength is equal to maximum tensile load divided by original cross-sectional area. Yield strength is the ability of material to resist the plastic deformation. It is the value of stress at which the plastic deformation of materials start. The point at which stress due to the strain suddenly increases is the yield point or yield stress. Yield strength is the ratio of load at the yield point to the cross-sectional area of the component. Moving forward to shear strength, it is the maximum value of tangential stress applied to shear it off across the resisting section. It determines the material to withstand forces acting tangential, causing crystal dislocation due to the relative movement of layers. Shear strength is the ratio of maximum tangential load to the original cross-sectional area. Compressive strength, it gives the detail regarding breaking power. For materials, it is the maximum value of compressive stress applied to break it off by crushing action. Compressive strength is the ratio of maximum compressive load to the original cross-sectional area of the component. These are all the mechanical properties of any material. Moving forward to the electrical properties, first one is the resistivity. It is defined as an electrical property of material that measures how strongly the material is going to resist electricity passing through it. It is directly proportional to the area of cross section of the material and inversely proportional to the length. It is defined by the symbol rho, that is proportional to the area and inversely proportional to its length. As we remove the proportionality constant, we have a proportionality constant value that is known as the resistance. So resistivity is equal to R A divided by L, where rho is the resistivity, R is the resistance of material, A is the cross-sectional area, and L is the length of the material through which current is trying to pass. Conductivity is next electrical property which is inverse of resistivity. It is an electrical property of material that permits or allows electricity passing through it. Conductivity is the reciprocal of electrical resistivity. It is defined as sigma, which is reciprocal of resistivity, that is rho, and it is equal to L divided by R into A. Dielectric constant is next electrical property. It is the quantitative measure of material to store electric charges. It is also defined as the ratio of capacitance of a capacitor in air to the capacitance of capacitor in vacuum. Sigma is equal to C divided by C0. C is the capacitance of capacitor in the air and C0 is defined as the capacitance of capacitor in vacuum. Next electrical property is dielectric strength and thermoelectricity. Dielectric strength is defined as the limitation of electrical field intensity above which breakdown occurs, that is, the insulators get ruptured or punctured. Increase of the thickness of material, increase in the time of application of electric current, and increase in humidity finally decreases the dielectric strength of the material. Thermoelectricity, it is defined as if two metals are joined at end by end and the junction is any one of the junction is gradually heated, then a small current in millivolt is produced, which is known as thermoelectric effect. This kind of thermocouples are made in the thermocouple pyrometer, photoelectric cell pyrometer, etc. etc. These are the electrical properties of materials. Moving further to thermal properties of materials, the very basic properties are melting point and freezing point. Melting point is the temperature at which solid changes into the liquid state. Metals and covalent compounds have sharp melting point, which helps to identify them. In case of polymers, the crystalline polymers have crystalline melting point temperature, that is represented as Tm, and for amorphous polymers only glass transition temperature exists, that is defined as Tg. Freezing point is the next thermal property. It is the temperature at which liquid changes into the solid state. Water freezes at 0 degree centigrade, that is 273 Kelvin. Different materials have different melting and freezing points. Property help in the processing of alloying of the materials. Moving forward to specific heat, it is related to the heat capacity. It is the heat absorbing capacity of material from its surrounding. It is defined as the quantity of heat required for raising temperature of unit mass of solid material by 1 degree. It may be represented by Cp or Cv. Cp is the specific heat at constant pressure and Cv is defined as the specific heat at constant volume. The amount of heat required for any material to raise temperature by 1 degree centigrade, that is dq, raised the temperature by some degree centigrade having with the temperature change of delta t, that amount of energy required, amount of heat required, dq is equal to m cp or cv delta t. From here we can define as Cp or Cv, that is the specific heat, is equal to dq divided by mass into temperature change. Moving forward to the thermal expansion, it is the tendency of materials to change its shape, size in response to a change in temperature. Thermal expansion may be 1D, that is a linear, 2D, that is the aerial, and 3D, that is the volumetric. The coefficient of thermal expansion is used to calculate the amount of expansion. Coefficient of thermal expansion as a linear thermal expansion, that is represented by alpha. Two-dimensional or aerial coefficient of thermal expansion, three-dimensional volumetric coefficient of thermal expansion are represented by beta and gamma respectively. Here, coefficient of thermal expansion in linear form, that is alpha, is defined as the change in length divided by original length into change in temperature. Coming to the next thermal property, that is the thermal conductivity, it is defined as the rate at which heat can flow through a material under uniform temperature gradient. Amount of heat required, dq is equal to K into cross-sectional area A into temperature gradient. Temperature gradient is basically defined as the change in temperature under with the ratio of the change in the distance traveled by temperature. Here the K is defined as the thermal conductivity. Thus the K is defined as dq into dx divided by area into change in temperature. Next, thermal properties of materials are refractoriness and heat resistance. Refractoriness is a special thermal property mainly related to refractories, metals and alloys. It is the ability of material to withstand high temperatures without appreciable deformation or softening under service conditions. It is measured in terms of piezometric cone equivalent, that is abbreviated as PCE. Heat resistance is next thermal property. It is the ability of material to withstand very high temperature. Generally, metals and alloys with high melting point have good heat resistance. Moving forward to the chemical properties, that comprises of composition, corrosion resistance, and next one, that is the coming to the composition of metal, any other materials, they made up of constituent atoms and their quantity or percentage. The composition of a material is generally given by the chemical formula, like alumina is given by Al2O3. Stainless steel structure is given by the presence of iron by 60 to 70%, chromium by 18%, 0.1 by 0.08%, and nickel from 8 to 24%. Corrosion resistance is very important chemical property of any material for being used in different applications. It is essentially the degradation of a metal by reaction with environment. Dry corrosion and wet or electrochemical corrosion are two main type of corrosion. Moving forward to the next chemical property as the crystal structure. The atomic molecular crystalline structure of metals, alloys and other crystalline compounds are experimentally found by X-ray diffraction, neutron diffraction and field ion microscopy technique. Body-centered cubic crystal, that is BCC, face-centered cubic crystal, that is FCC, and hexagonal closed-packed HCP are the important metallic structures used in study. For example, iron is a soft and ductile crystalline material in delta iron form, normally which exists in body-centered cubic crystal in the temperature range of 1400 degrees centigrade to 1539 degrees centigrade. Whereas the same thing exists in gamma iron form and with in FCC face-centered cubic crystal between the temperature range of 910 to 1400 degrees centigrade and in the nature as non-magnetic. The non-magnetic property start from 770 degree. That temperature is also known as the Curie temperature. Upon cooling below 770 degree, the iron further transform from gamma iron form to alpha iron form, and its crystal structure also changes from face-centered cubic crystal to body-centered cubic crystalline structure. Finally, these are the property related to chemical properties, and all the previous one from mechanical, electrical, physical, and thermal and chemical properties of the material. All these study materials have been prepared with the help of NPTEL lectures by Professor Satish V. Kailas from ISC Bangalore. W.D. Callister book, very useful, very important book of material science and engineering. V. Raghavan, Material Science and Engineering book, written by Professor V. Raghavan from former professor of IIT Delhi, and these have been prepared with the help of. Then I refer you for depth of knowledge to go with these books and the lecture series of NPTEL. Thank you so much for attending the lecture. Thanks a lot.